All right, says it's recording. This time it should be recording. Yeah, so we are going to jump for just these last two lectures. By the way, there's not going to be any reviewing for the final during class today or Thursday. That's the weekend. Because I want to have 2 full days to talk about chapter 14 in the book, which is actually the title of it is not Counting and Symmetries, but we're not going to have time to sort of do all of what's in this chapter. And so they put a big sophisticated title in there that's not really going to be meaningful for us. So I've made a more meaningful title for this chapter that you guys will be able to relate to, which is Counting and Symmetries, which is the way I would like to think about this. So just to get us back in the frame of mind for what we're going to do, let me remind you that last week we were talking about trying to color a graph and how many ways could we do that if we had k colors. So k is the number of colors, and the question is how many ways could we color the graph. And one of the easier scenarios for that is if you just have n vertices with no edges. So what we hopefully remember is that, well, then each vertex can be independently colored in any one of the k colors. So you'll have k choices for every vertex. The multiplication principle then just gives you k to the n ways of coloring the entire graph, right? And so just as a very explicit example of that, if I had a graph with exactly 4 vertices but no edges, and I was going to allow myself to use 2 colors, then we would have 2 to the 4th, which is 16 different colorings, right? There would be 16 different colorings here. But I have to ask you whether that really is what your common sense tells you. If the vertices are fixed in place and you cannot move them around, you cannot do any rotations or reflections or do anything to these vertices. If they're fixed in place, I think we could agree this is the right answer, right? There would be 2 choices for each of these 4 vertices, okay? But then I have to ask, but are all 16 colorings, are they all non-equivalent? I'll talk what I mean by that in a second. Are they all non-equivalent under symmetries? So just to give you an example of what I mean by that, let's suppose that I have the 4 dots here. And let's suppose I go, blue, 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 yellow. Guys, by the way, I almost lost my eyesight grading the last homework assignment with all the people were just doing the little dots on their graphs and stuff. I really need them to be huge dots. Either that or label them, please, with the letters there. And I'm really colorblind. I'm not kidding. So some people were using like a pink next to a light blue. And I was like, I cannot tell the difference. Like I really couldn't see the difference. So let's try this week to do a little better. Label your vertices with the colors you're going to use. So maybe B stands for blue. And I'll use Y for yellow. Doesn't really matter. But that would be, one way to color these 4 dots. But then the question is, I'll say versus. And I'm going to come over here and draw 4 more dots. And I'm going to maybe put the yellow in the upper left corner and the blue vertices around that. And so you can ask yourself, well, are these graphs really colored differently? Each of them has 3 blue vertices and 1 yellow vertex. It's simply a matter of the position that the yellow vertex is in. So I would say the answer here is no. Some of them are actually equivalent to each other. Like we wouldn't count them as being different. Some of them are equivalent. So let's make some notes about this. And what we actually would like to do is find out how many non-equivalent colorings there are. So out of these 16 colorings, many of them are equivalent already. So the question is, well, how many of them are actually non-equivalent? Maybe we should write that down just to kind of get the motivation for what we're going to do here in this chapter, kind of up in the front of the notes. So the the question that we're going to ask is, how many non-equivalent colorings are there for a graph? So maybe as a warm-up, let's go back to the 4 vertices here, and let's actually draw the full square. I'll actually add some edges here. So we could say, so for an example of this, consider a square. And it's going to be colored using blue, which I'll call as B, or yellow. So I'll just say B and Y, blue and yellow. Those are the colors that I can use. So, you know, what you could do is just enumerate or write out all of the different colorings. So one way to color this square would be to color all of the vertices blue. And there would be nothing else that's equivalent to that. Okay, because if you do any rotations or reflections or any kind of symmetries, or you move this thing around, it will still look the same as it does now, which is that it has 4 blue vertices. But if I had, let's kind of go back to the one that we had drawn over there. If I had blue, 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 and yellow in the lower left corner, that would be equivalent. That would be equivalent. Maybe I'll use a little twiddle to represent equivalent. That would be equivalent to a square where the yellow was in the upper left corner, and then blue, blue, and blue around that, which in turn would be equivalent to, I'm going to just draw all of them that are equivalent kind of together. So we could have put the yellow corner in the upper right corner, and the other 3 vertices are blue. Or finally, we could have put the yellow in the bottom right corner. And all of these ways of coloring the square would be equivalent in the sense, so these would not be equivalent in the traditional sense of P sub G of K. But if I consider them to be the same, if I can sort of achieve one of them by applying a symmetry to another one, right? So I could start with this one and do a 90-degree rotation and end up with this one. If I rotate another 90 degrees, I get here. 90 more degrees, I get here. So these are all equivalent. And in fact, if we had a necklace that had 3 blue beads and 1 yellow bead, right, there would really only be one way to make that necklace. There would not be 4 different necklaces. There would be just one. These would all get lumped together as a single non-equivalent coloring of that necklace. Okay, so what else could we have? So I did the picture with 4 blues. I did the various ways of coloring the necklace with 3 blues. So if I was kind of trying to go in order, I might think about doing the case of 2 blues and 2 yellows next. So if I have a square like that, I could have 2 blues and 2 yellows. And again, I'm going to think about how I could play with this figure and move the vertices into different positions. So I could do that 90-degree rotation again, right? And that would be an equivalent coloring. Or I could do it another time and the blues end up on the bottom and the yellows are up on the top now. Or I could do another 90-degree rotation and get the yellows on the right side and the blues on the left side. So I could do all of that. Let me just turn this screen off here, so I'll use that space in a minute. And you know, basically these are all of the ways, would you guys agree, these are all of the ways of coloring the 4 vertices where the blues are next to each other and the yellows are next to each other? Mm-hmm. There wouldn't be any other way to do it, right? You have to choose the two adjacent vertices to be the same color. So all of those really would just be the same necklace. Okay, but there's another way to get a necklace with 2 blues and 2 yellows that is not equivalent to this one, which is to do what?
Alternate them.
Yeah, alternate them, exactly. So put all of the I could put all of the blues on the diagonals and the yellows on the opposite diagonal, right? And you cannot achieve this necklace from any of those without like breaking the necklace, right? You can't just rotate or flip any of these necklaces to get this one. And same thing if I put the yellows on the top left and lower right and the blues on the top right and lower left. Those two would go together as well. Okay. Does that make sense? So there's another pair of equivalent necklaces that are not equivalent to anything else. We're actually making equivalence classes out of the 16 different colorings that we would have been able to do here. So let's keep going. The next scenario would be 3 yellows and 1 blue, which should be kind of a mirror image of what we had here. I will write them out just because I want to kind of have at least one example where I fully wrote out all the cases. So this could be yellow, 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 and then a blue in the lower left. Or equivalently, we could rotate that blue to the upper left and so on. Rotate it again to the upper right. Well, we're drawing some pictures today. 3 yellows and 1 blue. There's 4 different ways to organize those colors with the yellow sort of rotating around to all 4 of the vertices. So these are going to be equivalent to each other as well. Okay, and finally, we have all by itself just the one necklace where everything is red, is yellow, sorry, yellow. So everything is yellow, and that would be the last case. And let's see, we should have 16 pictures up on the board now. Should be 16 pictures, but as you can see, there are only, I think, 6 different necklaces here. Okay. Oh, I screwed this up, didn't I? Yeah, that last one should have 3 yellows. Thanks. Let's get our pictures right here. Let's get the blue in the lower right corner. I got them reversed. Just a little goof on my part, but that's what it should have been. Yeah, thank you. And so what we have is that there are 6 non-equivalent colorings. Let's just jot that down. There are 6 non-equivalent colorings of the square. Right, so there were 16 different colorings if we keep track of the different positions, but then if we allow ourselves to imagine rotating or reflecting this figure, then we would have only 6 different ones that we would want to be counting. So we haven't really done something like this in the first 13 weeks of the semester because, we're not sort of just counting things up to symmetry, right? And which is actually what we're trying to do now, which is kind of an interesting concept. So let's write down a definition here. I've been using some words that I want to make sure that we have in our notes and that hopefully will make sense to us. By the way, I mentioned a few minutes ago that the big theorem this week is the so-called Burnside's theorem. We'll mostly be looking at that on Thursday, but what it is about is it is a theorem that counts the number of non-equivalent colorings of a figure. So maybe by the end of the week, we should be able to get this answer without just drawing all the pictures out, but rather by using the theorem as well. So here's a definition that will be helpful for us. The book uses this sort of horseshoe-shaped thing. It's just capital omega. And this is, let omega be a geometric figure. So it is just some figure. It could be the square, like what we just have been looking at in the last example, or it could be something else. So a symmetry, I'm going to make the definition here, a symmetry of omega is a geometric motion. It is a geometric motion that brings omega back to itself. it's just some geometric motion. You take the figure, you pick it up, you twirl it around, you toss it like a frisbee, you go pick it up, and you set the vertices back down on top of where it was before. Okay, so you could take this square and pick it up, and you could do a bunch of symmetries to it. Does anybody know what the symmetries of a square consist of? One more time. The group D4. Yes. So I have a question. How many people in here have taken Math 302, the abstract algebra class? A few of you. So some of you have, or something equivalent to that. Basically, it's weird. This class has a prerequisite of 302 or 307. I'm like, well, if it took 307, that's good enough, but it doesn't cover what we need here. It's very, very baby group theory that we're going to need. In fact, it's so baby that I can more or less explain it to you on the spot, on the fly. And one thing that I eventually figured out how to do that would be more efficient than just writing it all on the board is I made a little handout that is the symmetries of a square. So let me just pass this out. Part of why I did this is because the book uses some kind of unmotivated notation for the different symmetries of a square. And I want us to be using the notation that's compatible with the book we're learning out of. So let me just send this along. If I can get them to come apart for me here. This is just it's kind of a through. Yeah, so you can see that as an example, and maybe I'll add this in the notes. By the way, there are a couple of people in Zoom. Do we need another one?
No, I have a question.
Okay, before you ask your question, there are a couple people in Zoom. I just wanted to mention this handout is in the final exam resources folder, and I will give it to you on the final. So you don't need to memorize this. And if you're watching at home, go into Canvas, you'll find this handout. Jose, what was your question?
It's like defining geometric motion as like a linear transformation.
It can be because rotations are linear and reflections are linear. So that is perhaps the sense in which Math 307 is which is a linear algebra course, is in the background of this as well. But I actually think that this is more suited to the group theory point of view, where we are just doing a single operation. In the case of a geometric figure, it's just a symmetry. Those are the operations that you're composing together. And so for a square, the symmetries form what is called the dihedral group. Again, if you aren't familiar with this, if you haven't taken any group theory at all, it's no worries. It's basically just going to be what's on this handout. And this is the dihedral group that I would denote it as D4. The 4 just coming from the fact that it's a 4-sided figure. So you could generalize this handout for a pentagon or a hexagon or a triangle or any of these other shapes. But the point being that you're looking at rotations and reflections. If you look at the handout, the 4 things on the left column are considered as rotations, either 0 degrees, 90 degrees, 180, or 270. And then the ones on the right, these are the reflections. And I kind of drew a little line to show what I'm reflecting along, so you can kind of try to understand it a little bit. To really get the hang of it, you have to label your square or whatever your figure is with sort of what the 4 corners are. So just as a quick example, I'll show you one example here. If I want to take the square and rotate it by 90 degrees, so that is what, so 90-degree clockwise rotation, that is what in the handout is denoted as rho sub 4. So that little p is pronounced rho, it's a Greek letter. And this just means take your square, pick it up, and rotate it by 90 degrees clockwise. And if you do that, what you want to pay attention to is that the labelings on the corners would then, shift around by 90 degrees. okay? And actually what happens when you do this is that you end up creating a permutation of the numbers 1, 2, 3, and 4. And you can actually denote this permutation in sort of a cycle notation. And again, if you took a 302 class or any kind of modern algebra class, you would have had a little more time to absorb this. But let me just basically give it to you in a notation that a permutation could often be written. I mentioned cycle notation. We actually aren't going to need that here. This is just what's called a two-line notation. And what you're going to do in this is this is a function that takes 1, 2, 3, and 4 and sends it to 1, 2, 3, and 4. It's a bijection. And all you're going to do is just kind of, you don't usually draw these arrows here, but I will for this first example. You just sort of say where these points move to. So if you rotate this by 90 degrees clockwise, the 1 will end up going over to here, which is where 2 is. So I can say 1 goes to 2. And the 2 will go to where the 3 is. The 2 goes to 3. 3 goes to where 4 is. So I put 4, and then the 4 goes to the position of where 1 is. So I could write it like that. That make sense? Now, that's not the only way to interpret this. You could be looking at this figure and say, oh, well, the 1 turned into a 4, and the 2 turned into a 1. So why, so 2 turned into 1, why am I writing 2 goes to 3? It's just a convention, and you just have to adopt one convention that you're comfortable with and just live with that. So the one that the book uses, and I actually also kind of tend to favor this one as well, is the one that's reflected by what I have on the right over here, which is that where does 1 move to? It moves to position 2. 2 moves to 3. 3 moves to 4, and 4 moves back to 1. Okay, so just be a little cognizant that there can be more than one way to kind of interpret that. Okay, so yeah, I used to write out all 8 symmetries in my notes here, and then I decided to make this handout and save us all a bunch of time, right? Another example, it would be a reflection. So maybe just we'll draw one more of them just to kind of appreciate this a little bit. So let's do the tau 2 reflection. Okay, and so what we can do, guys, is look at our handout. I drew this sort of diagonal line like this. If I label the corners again, 1, 2, 3, and 4, starting off like that, what this diagonal line means is that I'm just going to flip the square along that diagonal. And you can imagine that if you did that, what would happen is the 2 and the 4 are kind of the pinch point of the axis of symmetry. So they're just going to stay put. And what happens is the 3 and the 1 just swap places. And so if we wanted to write tau 2 as an actual permutation in this 2-line notation, the 1 goes to the 1 ends up moving to the position of 3, and 3 moves back to the position of 1, and the other 2 vertices just stay put. So you would just have that. Okay, now keep in mind that there are actually 24 permutations of the numbers 1, 2, 3, and 4. But this is a group of size 8. It's only 8. And they're all on the handout. There's 4 rotations and there's 4 reflections. You might wonder, well, where are the other 16 permutations? If these are 8 of them, then where's the rest of the 24 permutations? Well, of course, there are permutations that would break the square, that would break the figure. Like right now, the 1 and the 3 are not next to each other. Well, we could imagine a permutation that would send 1 and 3 to new positions that are adjacent, right? And so then there'd be an edge there. Okay, so, but that would require us to like completely disassemble the square and all the edges and then like start over. That we're not going to do. These are, sometimes we use the word rigid. This is a rigid figure and we're doing rigid symmetries. You're not allowed to like break or bend anything. You just have to kind of leave it as a solid object. And as long as you do that, you only have these eight symmetries here. Okay, great. Is everybody with me so far? What do you guys think? Pretty fun stuff? I like it when things come together. Combinatorics coming together with a little bit of modern algebra here is pretty sweet. So we're going to continue to play with that idea. I mentioned something earlier about equivalent colorings and non-equivalent colorings. I'd like to get a definition of that on the board now. Now that we have the group of symmetries kind of in our back pocket, we can use that to help us understand this concept of equivalent colorings. So let's do that. So definition over here. Two colorings of omega, which is our geometric figure. Two colorings are equivalent. They are equivalent if one coloring can be obtained from the other by applying a symmetry of omega. So if there is a symmetry that we can apply to take us from one coloring to the other, then those are equivalent colorings. And if we look back on the center board, I haven't erased it yet, like everything that's in one sort of big collection here, all of these colorings could be obtained from each other by applying a symmetry, in this case rotations, right? And it's important to know that it actually doesn't matter which, you're not really talking about a first coloring and a second coloring. It's a completely symmetrical, shouldn't use that word, concept. Because if it's possible for me to do a symmetry that takes me from here to here, then I will of course be able to do a symmetry that takes me back from this one to this one. Because in a group, every element has an inverse, and that inverse symmetry is exactly what will undo the original symmetry that you had applied. So we don't have to keep track of, well, which coloring is the first one and which one is the second one. It really doesn't matter. It's a totally symmetrical idea. It's not only is it symmetrical, it's also transitive. If the first coloring is equivalent to the second one, and the second coloring is equivalent to the third one, you just imagine 3 of these here, right? And if that's the case, then the first one is also equivalent to the third one, because you can just compose the symmetries together, which is just some other element of your group, right? So this is a transitive concept, it's a symmetric concept, and it's also reflexive, if you know that word. The point being that every coloring is equivalent to itself, because you can always just apply the identity element. Yeah, rotation by 0 degrees, where you just basically pick up your object and set it straight back down in the same spot. So guys, what I'm saying, for some of you who may have seen this before, this concept of colorings is reflexive, symmetric, and transitive. Does anybody know with those 3 properties what that's referred to as? One more time? Yeah, it's an equivalence relation, and you get equivalence classes here. So any 2 things that are kind of in the same equivalence class is just saying that, well, there's a symmetry that can take me from one to the other. And when you have equivalence relations, they always partition your set into non-overlapping subsets whose union is everything. And in this case, there's the everything is the 16 different colorings up here. And we have partitioned those 16 colorings into 6 non-overlapping equivalence classes for this square. Does that make sense? Yeah.
Yeah, one question. Would that definition not allow for composition
of 2 symmetries?
Yeah.
If you compose 2 symmetries together, right, you're just actually going to get another symmetry. So it actually would be perfectly fine if I see 2 colorings and I think, I can get from one to the other by composing two symmetries. Well, the fact of the matter is you could have taken those two symmetries and simplified it into a single symmetry by just using the group operation in the dihedral group in this case to do that. So yeah, we don't really have to worry about whether it was one symmetry or more than one symmetry or anything like that. Yeah. Okay, questions so far? Am I doing okay today? All right, so far so good. Let me write down a notation that we are going to find helpful for talking about colorings. So a coloring of omega can be written as, we can actually write it as a vector here. So you're going to see me do this. The coloring can be thought of as basically a list of colors that are arranged into a vector. So I might have a vector C of 1, C of 2, and dot, dot, dot up to C of, let's say, n, if my figure has n vertices on it or n things that I want to color. So this is just a list of colors. And you would need to have a convention for like what the first vertex was and what the second was and so on. So like this picture right here, this one could be considered to be colored as blue, blue. Let's say I go clockwise starting from the top left. Clockwise from the top left, so blue, 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 yellow. Whereas this one, if I go clockwise from the top left, this one would be yellow, blue, blue, blue. We're just kind of representing them as a vector. So each coloring can be just written as a vector. We don't actually have to draw the picture every time with the vertices labeled inside. We can just do that. Okay, does that make sense? There's no right or wrong choice about where the first vertex is or the second one. You just have to make a convention for that. Okay, and then another notation while we're at it here, kind of along the same lines, this is the right time to talk about it. The equivalent colorings, to the vector C. So if I have a coloring C, then you might ask yourself, well, which colorings would be equivalent to it? Well, there could be a bunch of them, so it's going to be a set. It's going to be a set of colorings, and what they are going to be is we're going to take, I'm going to denote this with little f, and then I'm going to use a star. I'll explain my notation in just a second, and we apply that to C. So the f here, so this is such that f is a symmetry of omega. F is a symmetry of omega. So I think this should just be totally compatible with the definition of equivalent colorings. Two colorings are equivalent if I can start with one of them and get to the other one by applying a symmetry. So I can take any one of my symmetries F of my figure and just apply the symmetry. So this little star just means apply the symmetry. The symmetry being F. So apply F to C. That's kind of what that star means. That makes some sense? Apply F to C, and you are talking about the equivalent colorings to C. When you do operations in, when you make a group out of these symmetries over here, guys, the operation that you are using is composition. So over here, let's just say under composition, going back in my notes here. And the composition, as you probably remember from your calculus days, is usually this little open circle for the composition of things. I don't want to use the open circle here. That's why I'm switching to an asterisk. Is because you're not putting two symmetries together. You're taking one symmetry and one coloring. And the coloring, the set of colorings is not a group. It's just a set. And if you go further in abstract algebra, what people will do is they'll talk about the group has an action on the set. The group acts on the set. It just means that, okay, so you take a group element, you take a set element, and it spits out another element of the set. But the set, in this case, the set of colorings, does not have any algebra structure to it. It's just a dead set. It's just sitting there. It's just a list of colorings, you know, the 16 colorings that we had earlier, right? It's just, there's no algebra to that, but we can sort of impose an algebra where the group elements act on the set. So you're taking a group element, you're taking a coloring, smash them together, you get another coloring. So that's kind of the way you can think about this. So far, so good? Yeah, so just as maybe we'll just do a quick example of this. I think there's some homework problems like this, so I might as well just do one or two really easy ones just to make sure we kind of get familiar with this. Let's suppose that we take the coloring. I'll stick with a square for now. We'll go with blue, yellow, which I guess if I use my clockwise ordering with starting in the upper left corner, that would be this coloring right here. Right, so this would be my coloring that I'm actually using. I can take row sub 4 and act on that coloring. And I would like to just understand how that would work. Row sub 4, remember, is my 90-degree rotation. So what happens is vertex 1, which is blue, moves to position 2. And you can see it over there, 1 goes to 2. So instead of writing 1 going to 2, now I'm just moving the blue from the first position to the second position. 2 goes to 3, 3 goes to 4, and the fourth one, which is yellow, goes back to the first position. So you end up with this one, which is actually the other equivalent coloring. And we did say that. The equivalent colorings are all going to be obtained by starting with one of your colorings and just hitting it over and over again with different symmetries. Now you might be thinking, oh, but wait, there's like 7 other symmetries I could use right now. But every single one of them will either produce that or that. So your equivalent colorings is only 2, right? Yeah, so it's the tricky part about it is that you feel like, oh, there should be 8 different things if I do all 8 symmetries on that coloring, but actually they sort of get glued together, like the results are kind of glued together because these are, you know, different symmetries can have the same effect on the colors. That's all I'm trying to say. Yeah. In fact, if you took the all blue necklace, every symmetry would just give you this again. And so you're not going to get anything more interesting than that. Okay. So far, so good. A little bit more notation here. Oh, I hate to lose these pictures. They're so helpful. Let me come back over here. We don't need this over here, I don't think. We've got the handout, right? So that's hopefully going to help a little bit. I want to talk about a couple of concepts that are actually very common in group theory, particularly when we're talking about actions of groups, which is the first one is called the stabilizer. So I'll make this as another definition. And it's called the stabilizer. So given a coloring C of my figure omega, okay, we are going to define the stabilizer of C, and this is denoted, so don't know that this is the world's best notation ever, but I'm going to use it because it's pretty standard, G of C. So this is going to be the stabilizer of this coloring. We define the stabilizer to be the following. The stabilizer of that coloring, my friends, it's the set of symmetries. It's the set of these little F's such that if you apply F to the coloring C, you just get C back again. You just get the same coloring back again. That is the stabilizer of the coloring. So let's maybe do an example of that. So you're fixing a coloring ahead of time, and then you're just asking which of your 8 symmetries, in the case of the square, which of your symmetries just leaves that coloring exactly the same. Okay, so as an example, maybe we take, let's take the same coloring I was using before over here, blue, yellow, blue, yellow. So we'll just take that one. And we have to run through the different symmetries of the figure, the square in this case, and write down which ones are going to leave this coloring exactly the same. So we've got our sheet. We might have to look at it. Keep in mind, by the way, that the identity element, which is, I called it I here on the handout, the identity element, which is the one where you just take the figure and pick it up and just set it right back down again exactly as it was, that will always fix every coloring. So the identity should be part of any stabilizer. Okay, but what other, which of these other ones, I want you to imagine, so blue, yellow, that's this one here, right? What could I do to this coloring in terms of these 8 symmetries that would leave the coloring, not an equivalent one, literally this one again. Yeah, Tim.
Tau 2.
The tau 2. So yeah, if I rotate, or sorry, if I reflect across this line, the coloring stays exactly the same. So I'll put tau 2 in there as well. Okay, I like it. Anybody see any others that would be fixed? Yeah, Kevin? Tau 1, which is actually, let's check that one, we're reflecting this way, right? So if you reflected along this diagonal, again, the coloring does not change. So that would be tau 1. And then is there anything else? Marcus?
Rho sub 4 squared, that's the 180 rotation.
Yeah, if we do a 90-degree rotation twice, we'll have a 180-degree rotation, which is what rho 4 squared would be. And you can see that if you were to rotate this 180 degrees, that you would still have the same coloring. Yeah, and would there be any others?
No.
I don't think so. I don't think so. Actually, so there's a little bit of a fact that is worth writing down here, which is that if you take any stabilizer of any coloring, it's a subset of the group of symmetries. In this case, it was 4 out of the 8 symmetries, but it always forms, this is especially for the 302 crowd, it forms a subgroup of the group of symmetries. Of omega. So it actually forms a subgroup. Meaning that it is a group in its own right. If you took any 2 of these and composed them together, you would stay within these 4. You wouldn't get the other 4, right? You know, you can kind of almost, well, you would have to actually do some calculations to check that. Like, what is tau 2 times tau 1, right? Composed with tau 1. You'd have to make sure that it was still one of these results here, but you could do that. You could do that. And the beautiful thing about that is that actually tells us that, actually, do you mind if the group of symmetries of omega, can I just call that G for a moment? Just, I want to use that notation. I don't think I have a notation for the group of symmetries yet. I mean, it's the dihedral group a lot of the time, but it doesn't always have to be that. A very important fact, in fact, I call it the most important theorem in finite group theory when I teach 302 or 407, is that the size of a subgroup always has to divide the size of the group. So, and that is something called Lagrange's theorem. Remember that? Oh, yeah. If you took 302, you would have seen that, or 407, something like that. You would definitely have heard about Lagrange's theorem. And so what this is just saying is that the size of any stabilizer always divides the size of the group of symmetries because it forms a subgroup. So if we see that we have 8 symmetries in our group, right? Then the stabilizer of any coloring should either have size 1 or 2 or 4 or 8. It has to be a divisor of 8. And that's kind of helpful because you're like, oh, well, I already have 4 symmetries here. If there were any more than that, the entire group would be the stabilizer of that coloring. Yeah, so obviously this depends a lot on which coloring it is. If we use the all blue coloring, then the stabilizer of that would be all 8 symmetries, okay? But the point is you can't get a stabilizer that has 5 or 6 or 7 symmetries in it. It's got to be a divisor of 8, which is pretty cool. Okay. Everybody with me so far? What I did here is I started with a fixed coloring, and then I asked myself, which symmetries would leave it the same? Of course, we can turn this on its head, and we can instead start with a symmetry of the figure. Okay, I'm going to rotate 90 degrees, something like that. We can start with a symmetry and then ask which colorings would be left unchanged by that particular symmetry. And we actually need to talk about that also. So I'm going to turn the conversation around, and instead of starting with a coloring and looking at the symmetries that fix it, I'm going to start with a symmetry and look at which colorings would be fixed by it. So that's going to be the second definition. Okay, we're really doing amazing. We're getting through a lot of this stuff. All right, awesome. So I just love this. You guys know I did my PhD work in abstract algebra, specifically ring theory, but then I actually have found that I'm more in love with group theory than anything. I work on projects with students usually more frequently in group theory than I do ring theory. So it's always fun for me to talk about this particular topic. Definitely enjoy it. So yeah, let's keep going. I'm just stoked. Make another definition here. Yeah, so given a symmetry F of my figure omega, so instead of given a coloring, now we're going to be given a symmetry. We define the following thing. It is going to be denoted script C of F. This is the book's notation. It's like a script C, like a you have good calligraphy, you can curl the ends of that C. The thing that is unfortunate about this is there is no good name for this. So unlike the stabilizer, which is a well-established standard piece of terminology, this one doesn't really have any particular name, but it's C of F. And this is the set of colorings C such that F star C is equal to C. So when you look at the condition, it is exactly identical to the one that we had over here. But over here, we were fixing the coloring first, and then the set consisted of the symmetries. This one is the other way around. We're fixing a symmetry first, and then we're looking at which colorings are fixed by it. So again, I obviously want to play with a quick example of this to get the idea. Let's do, let's let F be, maybe let's just pick tau 1. Okay, I'll just pick on tau 1 for a minute. And tau 1, if you go back to your little diagram that I have, and again, this is just literally coming from the book, tau 1 flips things along this diagonal. So the question would be, what would be the colorings that are fixed by that. In other words, what is script C of tau 1? Now, we have 16 different colorings of this square if we don't pay attention to anything, just have 4 dots, right? So the question would be, and this is going to be important, is like, how can we figure out what they would be? Would you guys agree that I can color the first and third vertex any way I want and I won't have any trouble because those 2 vertices are going to stay in place? Right?
Yeah.
The only thing that's important is whatever color you use on vertex 2 should be the same as the color that you use on vertex 4 because those 2 vertices are going to switch positions. Yeah. So when you're writing these out, the only thing you need to make sure about, guys, we're still going to use blue and yellow, but the second and fourth positions should always be the same. So I could do, well, blue, 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 blue. I'm going to write them all out. Okay, actually want to see them all spelled out. We could do blue, yellow, blue, yellow. Okay, the second and fourth positions are always the same. Now I'm going to go back and I'm going to do yellow, blue, blue, blue. And then I'll do yellow, yellow, blue, yellow. What I'm kind of doing in the first column, I'm doing the ones that have a blue in the second and fourth positions. And in the right column, I'm putting the ones that have yellow in the second and fourth positions. So I also have to consider blue, blue, yellow, blue. And then I have to consider yellow, blue, yellow, yellow. Oh no, that does not work. I just made a mistake. Sorry, that should have been blue, yellow, yellow, yellow. That's what I wanted to do. Okay, and then lastly, we would have yellow, blue, yellow, blue, and then yellow, 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 yellow. That should be 8 different things. Do you see why it's 8 things? Basically, guys, you have 2 choices here. You have 2 choices here. You make them either color you want. So you notice I've done every combination: blue and blue, yellow and blue, blue and yellow, and yellow and yellow. And for each of those, I now have only 2 choices for this pair of off diagonal vertices, right? Because they have to be the same. So 2 times 2 times 2. There's 8 different colorings that are going to be fixed by that particular symmetry. Does that make sense? Believe it or not, for the Burnside theorem, this kind of calculation is going to be even more important than the stabilizer one, because we're going to be seeing this script C of F in the theorem. So we definitely, this is the first of many times that we will be practicing this kind of calculation. Okay. Yeah, so I think I'm good with that. Any questions so far? Okay, I am ready to state a theorem now, I think. And this is not the big Burnside theorem quite yet, but this one will be very important, leading us to it. So I'm gonna write it down, and then Thursday will be my last class, and it'll be a chance for me to, well, kind of end on a bang. We'll get you guys motivated to come back one more time. But before we can get to that, I do have another theorem here that's quite important to state first. So this is theorem 14.2.1. We're already in section 2 of this chapter, after I've kind of breezed through the first part of it. So what does this say? Well, this just says let C be a coloring of omega. So I start off with a coloring again. So that's kind of in the same spirit as the definition of the stabilizer over here. And then I'm going to let F and G be symmetries of omega. Okay, so I'm going to let F and G be two symmetries of omega. So I've got a coloring and I've got a pair of symmetries. So then here is the statement of this result. I want to know in what scenario will the two symmetries have the same effect on my coloring. So when will applying G to C be the same as applying F to C? Now, the reason that I care about this, before I write the rest of the theorem, I just want to know, why do I care about this? So remember, guys, if I start with a coloring and I apply symmetries to it, I'm just obtaining other equivalent colorings. They're just equivalent, right? If I start with C and then I calculate F star C, that's just an equivalent coloring. And so is G star C. But that's not really ultimately what I'm going to care about. What I'm ultimately going to want to do is count non-equivalent colorings. That's what I'm ultimately hoping. How many different non-equivalent necklaces can I make out of yellow and blue beads? That's what I really am going to care about. But in order to count the non-equivalent colorings, I need to know sort of, how often am I getting the same coloring back when I apply different symmetries, right? Actually, the more times that F star C and G star C are the same, the less equivalent colorings you have. Let me say that again. The more times that these results are equal, for the more F's and G's that you can find, the more times that they are equal, that means you're getting and when I say equal, I mean equal. Equal as vectors, as coloring vectors, right? The more times that happens, that means that you're getting exactly the same necklace over and over again. You're not getting two different equivalent ones, right? So you're getting, the more times that these things are equal, then you actually are getting less different equivalent necklaces. Yeah, which means you'll have more non-equivalent ones, actually. So anyway, so that's why I kind of care about this. And the theorem is the following. It is just if and only if, and here I'm going to use a little group theory again, the inverse of F in the group of symmetries, that's the inverse element. So if I rotated 90 degrees clockwise, the inverse would be 90 degrees counterclockwise. I compose that with F, and this needs to be an element of the stabilizer of the coloring. Isn't that interesting? Okay, so that is the result here. That is the result. Okay. So the way I like to think about this, guys, is I like to imagine that the F is already kind of a fixed symmetry that I have in my hands. And I'm just trying to figure out, well, how many different G's would I be able to write down that would basically end up doing the same thing to the coloring that F did? So I have an F in my hands, and the question is, how many different G's could there be? Well, it turns out that if you know what this F is, and you want to know, well, how many different G's could you have? It's exactly as big as whatever the stabilizer is. If the stabilizer has 4 things in it, then there'll be 4 different G's that will bring this element into that stabilizer. So the size of the stabilizer has something to do with this. We've already commented that it divides the order of the group, but actually it's going to have a lot to do with counting the non-equivalent colorings as well. So I would like to prove this, but I don't know how much time I have. Oh, I have 5 minutes. Do you think I can do it?
How long is the proof?
What's that?
How long is the proof?
Yeah, I know. Why am I asking you guys? I'm gonna try. It's actually not very bad to prove this one. So I think I might just give it a shot. Okay, we'll see how it goes. I do have to prove 2 directions, so that's already, that means I only have 2 minutes per direction. So the pressure's already on. But let me try and do the forward proof here to begin with. So let's assume that G star C is equal to F star C. So I'm assuming that when I apply either F or G to C, I get the exact same coloring. And what I'm gonna do then, guys, I can see that eventually I wanna get F inverse composed with G. I'm just going to apply F inverse on the front of both sides, right? So I'm going to just take F inverse and star it onto G star onto C. And that's the same as F inverse star onto F star C. So I'm just applying the F inverse on the left of both sides here. So there's certainly not going to be anything wrong with that. If two colorings were the same before, then if I apply the same symmetry to them, it's still going to be the same afterwards. But what you have now done is you've taken your coloring C and you have done two actions on it back to back, right? You first applied G, then you applied F inverse. Well, you might as well just make that into a single. Somebody was asking me this earlier, could it be two symmetries kind of back to back? Well, that's the composition of those two symmetries applied to C on the left. And same thing on the other side, guys. We can take F inverse composed with F and star that with C. Oh, by the way, what is F inverse composed with F? For the group theory folks, if I take an element of a group and I compose it with its inverse, I end up getting the identity element. Exactly. So this is actually just the identity element. I'll draw it as an I applied to C. And what does the identity element? This is the element where you take your figure, you pick it up and you set it right back down without doing anything to it. What does that do to your coloring?
Keeps it the same.
Keeps it the same. So it's still C. So guys, take a look. What did we just end up with here? If we take F inverse composed with G and apply it to C, it stays as C. That looks like my stabilizer definition. My stabilizer is which functions, when I star them with C, just gives me C. That's what we're looking at. So that's in the stabilizer. So F inverse composed with G lives in the stabilizer of that coloring. Yeah, that's absolutely how the forwards direction goes. Okay, well, I did that pretty fast. Is everybody comfortable with that one? Let me go backwards. Actually, to go backwards is very much equivalent. You almost could just take the proof over there and just write it in reverse. Like, let's assume, I will write it out though, because I think it's nice to see it written. Assume that F inverse composed with G is in the stabilizer of C. I'm going backwards now. Well, this just means by definition that if I take F inverse composed with G and star it with C, it stabilizes it as C. Okay, so we would just come up with that. But then on the left side, this is just F inverse starred onto G starred onto C equals C. So far, so good. And now all I'm going to do is apply F in the front of both sides to get, well, I'm going to make the F inverse cancel if I put the F in the front of both sides, and then I'll get this thing here. Okay, so we're basically done. Apply F. So we'll have F star with F inverse starred with G composed with C. I have a lot of room here, guys, sorry. Equals F star C. And you can turn those stars into compositions. And the F composed with the F inverse is just the identity. And the identity composed with G is just G. So this is the end of the proof. So that is G star C is equal to F star C. Okay, so that should be pretty good. It was a little quick. The more important thing than the proof really is going to be to understand what it's saying. And I've already kind of said it once, but I'm going to say it again on Thursday. Because in order to get to the Burnside theorem, which is really where we're headed, we really kind of need to understand this a little bit better. So I'll write it down again on Thursday at the start of class. I'll talk us through it again without doing the proof again. I'll talk us through what it says. And then the very next thing we're going to do is Burnside's theorem. I'll write down the proof. which is one of the proofs you could choose to learn for the final. And then we'll do a few applications and a group work to practice it. And then we'll take a class picture. At the end of class. It's our last class. I always like to do that. So we'll just give you a heads up on that one. Thanks, guys, for being here. I really enjoyed this one, I have to say. Yeah, I enjoy all of them. Really hope this